equal to Q1 plus Q2 because we replace this 2 by the single capacitor. This electron is pushed to the second plate where the electron number is more. Therefore, the second plate becomes negatively charged. To store the charges or to build the charges further, the battery has to do work against this electric field. Hello everyone, I am Maitri, Faculty of Physics, Vidhyaashram, Temple of Excellence, Mysuru. So welcome to the session 5 of chapter 2, Electrostatic Potential and Capacitance. So far you have studied about the potential energy and potential in this chapter and also about the capacitor. Now in this session, let us discuss combination of capacitors. What is combination of capacitors or what type of combination we have? Combination is nothing but the arrangement of capacitors. We can arrange the capacitor as a series and parallel. What is series combination? If I have two capacitors connected one after the other such that the charge flow has a single path and each capacitor the charge flow is of same, then that combination is known as series combination. Then what is parallel combination? Parallel combination of two capacitor is nothing but I have a capacitor and you know that capacitor consists of two plates. One is positively charged and another one is negatively charged. The positively charged plate of one capacitor is connected to positively charged plate of second one. And the negatively charged plate is connected to negatively charged plate of second one. Then this combination where the two capacitors are connected between same points and has same potential, then that combination is known as parallel combination. So remember, in series charge remains constant and in parallel voltage remains constant and charge has two paths, charge 1 and charge 2. So this is the combination of capacitor. And why we need combination of capacitors? Because by this combination of capacitor we can obtain required capacitance, and by the series combination we can increase voltage, and by this parallel combination we can increase charge according to the requirement of electrical circuits. So that we need to know this combination, that is series combination and parallel combination. Now let us first consider the series combination. In this, the question might be like this: derive an expression for equivalent capacitance of two capacitors in series. So question is derive an expression for equivalent capacitance of two capacitors in series. So let us consider two capacitors in series means end-to-end connection, two or more capacitors connected end to end is nothing but series. In that the charge flow as single path and the same charge flow in all the capacitors, same charge flow in all the capacitor. And for the first capacitor, the capacitance, you know what is capacitance? It is the ability of the capacitor to store charge. Let us consider it as C1 and for the second one as C2. And they are not connected between the same 2 points. Therefore, the potential difference across the first one as V1 and across the second one as V2. After writing this diagram, you have to draw diagram for the equivalent capacitance next to this. And this symbol represents the equivalent to this two capacitor. The single capacitor which replaces this two capacitors is known as equivalent capacitor, and we have arranged this in series. Therefore, let us consider the single capacitance as CS. As this single capacitor replaces this two capacitor, so same charge Q flows in this capacitor and across this the potential is V. So what is CS? CS is the capacitance. Capacitance of equivalent capacitor in which combination? In series combination. In series. Now, what is equivalent capacitor? Equivalent capacitor is a equivalent capacitor is a single capacitor. Is a single capacitor. A single capacitor. Observe the picture. This is the equivalent capacitor, which is a single capacitor. One capacitor that produces same effect as that produced by combination. Yes, combination. So this is equivalent capacitor, and this sentence is compulsory in the answer. You must not skip this sentence. While deriving the expression for equivalent capacitance in series or parallel, this sentence you have to write compulsorily. Then you start deriving. So in this diagram, observe here the voltage V1, V2 is equal to V when we replace this two capacitor by a single capacitor. Voltage V is equal to V1 plus V2. The V is the potential difference across the equivalent capacitor, which is equal to the capacitor in combination. Now, what is V is equal to? From the capacitance C, we have Q by V. From this V is equal to Q by C. So, what is the expression for V in terms of Q and C? As we have only Q and C in this diagram. So, V is equal to Q by C and Q by C. Q in all same, but the C changes. This V is for single capacitor, where we have considered S for the C, where S stands for series combination. Yes, next V1 is given by Q by C1 and V2 is given by Q by C2. In this, Q is common. Q by Cs is equal to Q of 1 by C1 plus 1 by C2, and Q cancel. Therefore, 1 by Cs is equal to 1 by C1 plus 1 by C2. This is the expression for the equivalent capacitance in series combination. And to find Cs, 1 by Cs is equal to C1, C2 and C1 plus C2. Now we need Cs, therefore Cs is equal to C1, C2 by C1 plus C2. So if you have two capacitors in series and if you want to find the equivalent capacitance of this combination, then you have to use this formula, which is Cs is equal to C1 C2 by C1 plus C2, or else you can stop here. You can stop the derivation where 1 by Cs is equal to 1 by C1 plus C2. C1 and C2 are the capacitance of two capacitor and Cs is the capacitance of the equivalent capacitor. The next combination is capacitors in parallel, and you know what is parallel combination, where two capacitors are connected between 2 points, same 2 points. Yes, same 2 points where charge divides as Q1 and Q2, but the potential remains same as they are connected between the same 2 points. And let us consider the capacitance of first capacitor as C1 and the second one as C2. The equivalent capacitance is Cp. The charge in this is Q and the potential in this is V. Yes. In parallel combination, the potential remains same, but the charge divides. Now, what is equivalent capacitance? Equivalent capacitance or the capacitor which replaces this two capacitors in parallel and produces same effect as that produced by the combination. Now, what quantity is divided? Consider that here the charge is divided. This charge is equal to Q1 plus Q2 because we replace this two by the single capacitor. And what is Q is equal to? By the expression C is equal to Q by V, we have a Q is equal to CV. So, what is Q is equal to? CV plus CV. And this is for equivalent capacitor whose capacitance we have considered as Cp and the potential is V. And for the first one, C1, potential is same. For the second one, C2 and the potential remains same. Now, in this potential common, C1 and C2 inside the bracket, and in the LHS, Cp into V, V gets cancelled. Therefore, Cp is equal to C1 plus C2. This is the capacitance in parallel combination. So, if you want to find a equivalent capacitance for parallel combination, the formula is C1 plus C2. Yes. Now you know the combination of capacitors. Now you know about the combination of capacitors, that is series and parallel. Now let us discuss the last topic of this chapter, that is energy stored in capacitor. Energy stored in capacitor. Let us discuss in what form the energy stored in the capacitor. For that, you consider first a neutral, that is uncharged capacitor. The charge on this is equal to 0. uncharged capacitor. Initially, you have to consider an uncharged capacitor. Now, connect this capacitor to a battery. Observe the symbol of the capacitor and the battery. In battery, we have two lines with different length, but the capacitor is represented by two parallel lines of same length. Yes. When battery is connected to uncharged capacitor, this battery pulls electrons from one plate, the plate from which the electron is removed, that becomes positively charged, and this electron is pushed to the second plate where the electron number is more. Therefore, the second plate becomes negatively charged. Now, the plates have the charge and they develop electric field. Because of this electric field, the battery has to do work to store the charges or to build the charges further. The battery has to do work against this electric field. Therefore, that work is equal to the energy. So, first to find the energy, we need to find out the work done by the battery. So, work done for small amount of charge dq on the plate is equal to potential into charge. As by the definition of potential, work done by charge is potential. From this we have the work done. Now, what is potential is equal to? Potential by the capacitance expression, that is C is equal to Q by V. V is equal to Q by C. So, in the place of V, consider Q by C dQ. Yes, this is for storing the small amount of charge by the battery on the capacitor. For the further storage of charges or to build the charges on the capacitor, battery has to do work against this electric field. Let us consider from 0 to store the charge to Q amount, the total work done to store charge from 0 to Q. Work done to store charge Q. Work done to store charge Q on the capacitor. We have to integrate the small work done dW, which is equal to integration of Q by C dQ from 0, that is uncharged capacitor, to charge on the capacitor Q. That are the limits of this integration. Yes. Integration of dW is W, and in this the capacitance is constant. Now integrate 0 to Q dQ. What is the formula for the integration of Q dQ? You already know this, as we have used this in chapter 1. Like, this is in the form of x to the power of n dx, which is equal to x to the power of n plus 1 by n plus 1. Now, integration of Q dQ, where Q has the power 1, is equal to Q power is 1 plus 1 by 1 plus 1, which is equal to q square by 2. So what is the answer for integration of q dq? The answer is q square by 2. So replace this by the answer. So work done is equal to 1 by c, and integration answer is q square by 2 from 0 to q. After integrating, you have to apply the limits. First, always upper limit means the q value always upper limit. Here the upper limit is q, and q value next is lower limit, that is 0. Between this two, minus. This is the procedure to apply the limits. So in the next step, work done is equal to 1 by c. Upper limit is q square by 2 minus lower limit is 0 and by 2, which we have in the denominator. Yes, now this answer is 0. Then the final work done is equal to q square by 2c. This is the total work done, which is equal to q square by 2c. By definition, this work done is nothing but energy stored as electrostatic potential energy. Therefore, W is replaced by U. U is equal to Q square by 2C. So, what is the expression for the energy stored in capacitor? Energy stored in capacitor. The expression is U is equal to Q square by 2C, where Q is the charge, C is the capacitance, and U is the electrostatic potential energy. Yes. And if I consider Q in terms of C and V, then the potential energy expression, let us check it. So what we have potential energy as Q square by 2C. Now in the place of Q, if I consider CV, U is equal to Q. In that place, I have to consider C square V square by 2C. One of the C get cancelled. Then another expression for potential energy in terms of capacitance and voltage is half CV square. So according to the given data in the problem, you have to use the formulas. So in problems, the data might be in terms of charge and capacitance, then you have to use this. Or the data given might be capacitance or voltage, then you have to use this expression for the energy stored in capacitors. And here the chapter ends. In the next session, let us solve the problems from this chapter. Thank you.